everyone, welcome back to the channel. Today we're diving into a groundbreaking paper titled, "An Image is Worth 16 by 16 Words, Transformers for Image Recognition at Scale." Ever wondered if the same tech that powers language models could revolutionize how computers see images? Stick around to find out. Transformers have totally dominated natural language processing, but in computer vision, everyone's still hooked on convolutional networks or CNNs. They often mix attention with CNNs or tweak parts of them. But what if I told you that's not necessary? This paper shows that a pure transformer, working directly on sequences of image patches, can crush it in image classification. When trained on huge datasets and tested on benchmarks like ImageNet, it not only matches top CNNs, but does it with way less computing power. Imagine training faster and smarter. That's the power of Vision Transformer, or ViT. In NLP, transformers are the rock stars, handling everything from translation to text generation. The secret? Pre-training on massive text data, and then fine-tuning for specific tasks. Thanks to their efficiency, we've seen models with over 100 billion parameters, and performance just keeps getting better without slowing down. It's like they've unlocked endless potential, no saturation in sight. But over in computer vision, CNNs have been the king since the early days. Inspired by NLP's wins, some researchers tried adding self-attention to CNNs or even replacing convolutions entirely. However, those attempts haven't scaled well on modern hardware because of complex attention patterns. So for big image tasks, good old ResNet-style models still rule the roost. It's a classic case of, if it ain't broke, don't fix it. But this paper is about to challenge that. So how do they do it? They take a standard transformer, yes, the same one from NLP, and apply it directly to images with minimal changes. First, they chop the image into patches, like breaking a picture into puzzle pieces. Then, they treat each patch as a word in a sentence, feeding their embeddings into the transformer. They train this setup for image classification in a supervised way. It's a bold move, treating vision like language. Now, when trained on mid-sized datasets like ImageNet, without extra tricks, these models don't immediately shine. They lag a bit behind ResNets. Why? Because transformers don't have built-in assumptions that CNNs do, like recognizing local patterns easily. But don't write them off yet. This is just the starting point for something bigger. So what's the big deal with CNNs? They have these built-in assumptions like handling translations and focusing on local areas, which helps them learn from small datasets. But ViT doesn't have that, so it struggles when data is scarce. But here's the twist. When you train ViT on huge datasets with millions of images, it totally flips the script. All that data overpowers the need for those built-in biases. ViT ends up matching or even beating the best CNNs on major benchmarks, hitting over 88% accuracy on ImageNet and doing great on other tests too. Transformers started in language tasks like translation and blew everyone away. Models like BERT and GPT got super smart by pre-training on tons of text and then fine-tuning for specific jobs. This set the stage for using transformers in vision. Imagine trying to make every pixel in an image pay attention to every other pixel. That would be a computational nightmare because it scales horribly. So researchers tried workarounds, like only focusing on local areas or using sparse attention. These methods showed promise, but were really complex to build and run efficiently. One model did something similar to ViT by using small patches and full attention, but it was limited to tiny images. ViT takes it further by showing that with massive pre-training, simple transformers can outdo CNNs and handle bigger images too. People have also mixed CNNs with attention to boost performance in tasks like object detection or video analysis. It's like giving CNNs a brain upgrade, but ViT skips the CNN part entirely and still wins. There's another model called IGPT that uses transformers on pixels after shrinking the image, training it to generate images, and then fine-tuning for classification. It got decent results, but not as high as ViT. Using bigger datasets beyond ImageNet is a game changer. Previous studies with CNNs showed that more data means better performance, but ViT applies this to transformers, proving they can scale up and transfer knowledge effectively to new tasks. Ever wondered how a vision transformer actually processes an image? This figure shows the whole setup. It starts by breaking the image into patches, then projects them into embeddings, adds position info, and feeds them through a transformer encoder. There's a special class token added that helps in classifying the image, like identifying if it's a bird or a car. The transformer uses multi-head attention and MLP layers to understand the relationships between patches, all without any convolutions. It's like teaching a model to see by focusing on parts of the image and how they connect, which is super efficient with large datasets. Here's the breakdown of that figure. The image is split into fixed patches, each gets embedded linearly, and position embeddings are added to keep track of where each patch is. This sequence goes into a standard transformer encoder. For classification, they add an extra learnable token at the start, and the output from that token becomes the image representation. This setup is inspired by NLP transformers but adapted for vision, making it straightforward to scale up without complex changes. Why stick to the original transformer design? Because it's simple and proven in NLP, so you can use existing efficient code almost directly. This means less hassle in implementation and better scalability, letting the model focus on learning from data rather than complex architecture tweaks. How does ViT handle 2D images? It reshapes the image into a sequence of flattened patches. Each patch is like a small piece of the image, and these are projected into a fixed size embedding. This turns the image into a list of tokens that the transformer can process, similar to how words are handled in language models. The number of patches depends on the image size and patch resolution, making it flexible for different inputs. To perform classification, a learnable class token is added at the beginning of the sequence. After the transformer processes everything, the output from this token represents the whole image and is fed into a classification head. During pre-training, a small neural network with one hidden layer is used, and for fine-tuning, it's simplified to a single linear layer, making it adaptable for various tasks. How does the model know where each patch is located? Position embeddings are added to the patch embeddings to preserve spatial information. They use simple, learnable 1D embeddings because fancier 2D versions didn't show much improvement. This helps the transformer understand the layout of the image without extra complexity. What's inside the transformer encoder? It has layers of multi-headed self-attention and MLP blocks, with layer normalization and residual connections applied at each step. This setup allows the model to focus on different parts of the image simultaneously and build up representations through multiple layers, ensuring stable and efficient learning.
We are Genapad. Your likes and subscriptions inspire us to create more videos and keep improving our service. Want to turn your own content into videos? Visit us at www.genapad.com.
The MLP in the Vision Transformer has two layers with a GEL-U activation function, which helps introduce nonlinearity for better learning without the complexity of convolutions. This formula represents the initial embedding of image patches combined with position embeddings, setting up the input for the transformer to understand both the content and spatial arrangement of the patches. This equation shows how multi-head self-attention is applied with layer normalization and residual connections, allowing the model to focus on different parts of the image simultaneously and stabilize training. Here, the MLP block processes the output with layer normalization and residual connections, refining the features learned by the attention mechanism for more accurate predictions. Did you know that vision transformers have way fewer built-in assumptions about images compared to CNNs? CNNs are designed with locality and translation equivariance in every layer, meaning they naturally handle shifts and local patterns. But in ViT, only the MLP layers are local and translationally equivariant, while self-attention is global. The 2D structure is barely used, just when splitting the image into patches and adjusting for different resolutions. Position embeddings start with no spatial info, so the model has to learn all spatial relationships from scratch, making it more flexible but needing more data. In a hybrid model, instead of using raw image patches, you can feed feature maps from a CNN into the transformer. This combines the strengths of both. The CNN extracts local features, and the transformer handles global context. The patches can even be one by one, which just flattens the feature map. Then, you add the class token and position embeddings as usual, blending convolutional efficiency with transformer power. After pre-training on big data sets, ViT is fine-tuned for specific tasks by replacing the prediction head with a new layer for the target classes. It often works better at higher resolutions because keeping the same patch size increases the sequence length. ViT can handle this, but the pre-trained position embeddings might not fit, so we interpolate them based on the original 2D positions. This interpolation is one of the few times we manually inject 2D structural bias into ViT, keeping it adaptable. In experiments, we compare ResNet, ViT, and hybrid models to see how they learn from different amounts of data. ViT shines by achieving top results on recognition tasks with less pre-training cost. We also explore self-supervised learning, showing that ViT has great potential for future advancements without needing labeled data. For datasets, we use ImageNet with 1.3 M images, its larger version with 14 M images, and JFT with a massive 303 M images to test scalability. After removing duplicates, we transfer the models to benchmarks like ImageNet, CFR, and others to evaluate performance across various tasks, ensuring fair comparisons. Ever wondered how big these vision transformer models really are? Let's break down the key specs. The base model has 12 layers, 768 hidden units, and 86 million parameters, while the large version doubles the layers to 24 and jumps to 307 million parameters. The huge model goes even further with 32 layers and a massive 632 million parameters. More layers and hidden size mean the model can capture more complex patterns, but it also needs way more computational power to train. How do we test if these models can handle real-world challenges? We use the ViT-AB benchmark, which throws 19 different tasks at them with only 1,000 training examples each. It's split into 3 groups: natural images like pets and everyday scenes, specialized ones from medical or satellite data, and structured tasks that need geometric smarts. This really pushes the models to adapt quickly with minimal data. Did you know the vision transformer sizes are borrowed from BERT in NLP? That's right, the base and large models are straight from BERT. And they added a huge one for extra power. They use shorthand like VL/16 to mean the large model with 16 by 16 image patches. Smaller patches mean longer sequences for the transformer to process, making it more expensive to run, so it's a trade-off between detail and cost. To make fair comparisons, they tweaked ResNet CNNs by swapping batch normalization for group normalization and using standardized convolutions, calling it ResNet bit for better transfer learning. For hybrid models, they feed ResNet features into ViT, treating each feature as a patch. They even played with sequence length by adjusting ResNet stages. Longer sequences mean a pricier ViT but potentially better performance. Training these giants is no joke. They used Atom Optimizer with a big batch size of 4096 and high weight decay to prevent overfitting, which helped in transfer tasks. For fine-tuning, they switched to SGD with momentum in smaller batches and boosted resolution for bigger models. They even used model averaging to smooth out the results, making the training stable and efficient. How do we measure success? They look at fine-tuning accuracy, where the model adapts fully to a new dataset, and few-shot accuracy, which uses a quick math trick to predict labels from frozen features without full training. Few-shot is great for fast checks when fine-tuning takes too long, giving a snapshot of how well the model generalizes on the fly. Time to see how ViT stacks up against the best CNNs out there. They pit their largest models, ViT-H/14 and ViT-L/16, against BIT, which uses big ResNets, and Noisy Student, a semi-supervised efficient net that's top on ImageNet. All were trained on powerful TPU hardware, and they track compute time in core days to see who's more efficient. The results are mind-blowing. ViT-L/16, trained on the same huge dataset, beats BL on every task while using way less compute. And ViT-H/14 pushes it further, especially on tough datasets like ImageNet and CIFAR 100. This shows that with enough data, ViT not only matches but surpasses CNNs without all the convolutional baggage. Hey everyone, check out this table comparing different models on image classification tasks. It's packed with accuracy scores and computational costs. For example, vision transformer models like ViT-H/14 and ViT-L/16, trained on huge datasets, are crushing it on benchmarks like ImageNet and CIFAR 100 with over 90% accuracy. But here's the kicker. They do this using way less computing power, sometimes just a fraction of what ResNet or Noisy Student models need. This shows that transformers aren't just for language. They're super efficient for vision, too, when you feed them enough data. All right, let's dive into Table 2. It's all about how vision transformer models stack up against the best in image classification. When pre-trained on massive datasets like JFT300M, ViT not only beats ResNet baselines in accuracy across the board, but does it with much less pre-training compute. Even with a smaller public dataset like ImageNet 21K, ViT holds its own, proving you don't always need the biggest data to get great results. This is huge because it challenges the old idea that CNNs are the only way to go for vision tasks. Now, look at this bar chart breaking down performance on the VTAB benchmark. It splits tasks into natural, specialized, and structured groups. ViT-H/14 is leading the pack, especially in natural and structured tasks, where it outperforms models like BIT-L. For specialized tasks, the top models are neck and neck. What does this tell us? ViT is really good at generalizing across different types of images, making it a versatile choice for real-world applications. So even though ViT models use less compute for pre-training, we have to remember that efficiency isn't just about the architecture. Things like the training schedule or optimizer settings can play a big role too. But here's the cool part. ViTL/16, trained on ImageNet 21K, still performs well on most datasets and can be trained in about 30 days on standard cloud hardware. That makes it accessible without needing supercomputers, which is a game changer for many researchers. This figure breaks down the VTAB tasks into groups and compares ViT to other state-of-the-art methods. ViTH/14 comes out on top in natural and structured tasks, beating models like ViT and others. For specialized tasks, it's a close race. Why does this matter? It shows that ViT isn't just a one-trick pony. It adapts well to various challenges, from everyday photos to more complex images, thanks to its transformer design. Ever wondered how much data ViT really needs to shine? Since it has fewer built-in assumptions than CNNs, the dataset size is crucial. The researchers tested this by pre-training on different sized datasets, small, medium, and large. On the smallest one, larger ViT models actually underperform, but as you scale up the data, they start to dominate. This highlights that without those CNN biases, ViT relies heavily on big data to learn spatial relationships effectively. In these experiments, they pre-trained ViT on datasets from ImageNet to JFT300M and tweaked regularization to boost performance. On the smallest dataset, bigger ViT models didn't do well, even with adjustments. But with ImageNet 21K, they caught up, and only with the massive JFT300M did the largest models show their full potential. This teaches us that for ViT, size matters. Both the model and the dataset need to scale together to unlock top performance. Ever wondered how vision transformers stack up against traditional CNNs as you feed them more data? This graph shows the accuracy on ImageNet for different ViT models and a CNN called beat plotted against the size of the pre-training dataset. You can see that with smaller datasets like ImageNet, BIT does better. But as you move to huge datasets like JFT300M, the larger ViT models like ViTH/14 and ViTL/16 start to dominate. It's a clear example of how ViT needs big data to shine, while CNNs have a head start with their built-in assumptions. Here's another graph focusing on how performance changes with the number of pre-training samples from the JFT dataset. It compares ViT models like ViTL/16 and ViTB/32 against ResNet CNNs. The ViT models start off worse with fewer samples but improve dramatically as the data grows, while ResNets plateau earlier. This highlights that ViT is like a sponge. It soaks up information from massive datasets to outperform others, making it a game changer if you have the data. Did you know that ViT models can actually beat top CNNs when trained on enough data? This figure illustrates that on ImageNet, smaller ViT models underperform compared to bit ResNets with limited pre-training data. But once you scale up the dataset, the larger ViT variants take the lead. It's all about data size. ViT's lack of built-in biases means it needs more examples to learn, but when it does, it excels. In this figure, we look at few-shot learning on ImageNet, where models are tested with very little data. ResNets perform better with small pre-training datasets but hit a ceiling quickly, while ViT keeps improving as the dataset grows. Even a smaller ViT variant like ViTB shows this trend. This suggests that for massive datasets, ViT's ability to learn from scratch gives it an edge, making it ideal for scalable AI applications. What happens when you compare architectures based on how much computing power they use? This graph plots accuracy against total pre-training compute in exaflops for vision transformers, ResNets, and hybrid models. Vision transformers generally achieve higher accuracy than ResNets for the same computational budget. Hybrids, which mix CNNs and transformers, do better for smaller models, but that advantage disappears as models get larger. It shows that pure transformers are not just efficient, but highly effective when scaled up. Here's a deeper dive into performance versus compute. Vision transformers outperform ResNets when given the same computational resources. Hybrid models bridge the gap for smaller sizes, but for larger models, pure transformers catch up and even lead. The shaded area represents bit models, which beat ViT on ImageNet with smaller datasets, but ViT overtakes with larger ones. It's a testament to ViT's scalability. More compute and data unlock its full potential. How do ViT models handle different dataset sizes without extra tricks? The researchers train them on subsets of the JFT dataset, from 9 million to 300 million images, using the same settings to focus on model properties alone. ViT models overfit more than ResNets on small datasets, like ViT-B/32 performing worse than ResNet, 50 on 9M samples but better on 90M+. This reinforces that CNNs have useful inductive biases for small data, but for huge datasets, ViT learns patterns directly and can be more beneficial, showing its data-hungry nature. The few-shot results on ImageNet and low data performance on ViT-AB are really promising for transferring knowledge with minimal data. This opens up exciting future work to explore ViT's capabilities in few-shot learning, potentially making it a go-to for tasks where data is scarce, but intelligence is key. Ever wondered how different AI models stack up when you give them tons of data? In this scaling study, researchers tested vision transformers, ResNets, and hybrid models using the massive JFT300M dataset to see how performance relates to pre-training cost. They included various sizes like ViT-B/32 and ViT-H/14, trained for different epochs, and hybrids that mix ResNet backbones with ViT. The goal was to find out which models give the best bang for your buck without being limited by data size. Check out the graph in the paper. It plots transfer performance against pre-training compute, and the results are eye-opening. Vision transformers crush ResNets in efficiency, needing 2 to 4 times less computing power to hit the same accuracy across multiple datasets. Hybrid models do a bit better at small scales, but that advantage disappears with larger models. Surprisingly, even though CNNs have local processing, ViT doesn't rely on it as much when scaled up. And the best part? Vision transformers keep improving without hitting a ceiling, hinting that bigger models could achieve even more. Let's peek inside the vision transformer to see how it makes sense of images. The first layer takes those image patches and projects them into a lower dimensional space using learned filters. When researchers analyzed these filters, they found they act like basic building blocks, similar to how you might break down a complex shape into simple patterns. This helps the model capture fine details in each patch right from the start, setting the stage for deeper understanding. After projecting the patches, the model adds position embeddings to remember where everything is. It turns out the ViT learns to encode spatial relationships on its own. Patches that are close together have similar embeddings, and you can even see a grid-like structure emerge. This means the model naturally figures out the 2D layout of the image, which is why custom 2D embeddings don't add much. Pretty smart, right? Self-attention in ViT lets it look at the whole image at once, even in early layers. Researchers measured how far information travels, like the receptive field in CNNs, and found that some attention heads focus on almost the entire image from the get-go. Others stay local, similar to what early CNN layers do. This mix of global and local focus helps the model build a comprehensive understanding as it processes the image. In the deeper layers, the attention becomes more global, with the model focusing on parts of the image that are key for classification. Hybrid models, which start with a ResNet, show less of this localized attention early on, suggesting ViT's approach mimics CNN's, but in a more flexible way. This ability to zoom in on semantically important regions helps ViT make accurate predictions without being rigid. The figure shows examples of how the output token pays attention to different parts of the input image. It highlights areas that are crucial for the model's decision, like focusing on a dog's face in a photo. This visual insight helps us see that ViT isn't just processing pixels randomly, it's intelligently picking out what matters most for the task. Transformers have rocked natural language processing, and a big reason is self-supervised pre-training on huge datasets. This approach allows models to learn general patterns without labeled data, making them highly scalable and effective. For vision tasks, applying similar large-scale self-supervision could unlock even greater performance, just like it did in NLP. Ever wondered how vision transformers actually see images? Let's break down this figure. On the left, we have filters that start processing the raw RGB colors in image patches, kind of like learning the basic building blocks of vision. The center part shows how the model remembers where each patch is located by comparing position embeddings, which helps it understand spatial relationships without convolutions. And on the right, we see how different attention heads in the network focus on areas of the image as we go deeper into the layers. Some heads pay attention to nearby patches early on, while others look at the whole image later, showing how ViT learns to combine local and global information for better recognition. This visualization proves that ViT isn't just guessing, it's intelligently focusing on what matters in the image. What if we could train vision transformers without labels, just like in language models? The authors tried a cool, self-supervised method where they hide some image patches and make the model predict them, similar to how BERT works in NLP. For a smaller ViT model, this boosted ImageNet accuracy by 2%, which is a solid jump, but it still lags behind supervised training by about 4%. This hints that self-supervision has huge potential to make ViT even better, without needing tons of labeled data. They're leaving other advanced techniques like contrastive learning for future work, so stay tuned for more breakthroughs. So what's the big takeaway from the vision transformer? It's all about simplicity and scale. Instead of baking in complex rules like CNNs do, ViT just treats an image as a sequence of patches and runs it through a standard transformer, the same tech used in language models. With enough pre-training data, this straightforward approach not only matches, but often beats top CNNs in image classification, and it does it with less computational cost. That means you can train powerful models without breaking the bank, making ViT a game changer for scalable AI vision. But hold on, the journey doesn't end here. The authors point out that ViT needs to tackle other vision tasks, like object detection and segmentation, and early signs are promising. Also, self-supervised pre-training shows improvements, but there's still a gap to close compared to supervised methods. And of course, scaling ViT even bigger could push performance further. So while ViT is already impressive, there's plenty of room to grow and innovate in the future.